Hey guys, we're going to be talking about solutions and gas laws in this unit. We're starting with solutions and looking at molarity, and we're going to be talking about this glorious thing here. What I'd like for you to do is a little bit unconventional. You're going to be taking some notes during this section, but I also want you to be doing some vocabulary note cards, okay? These are the terms that you're going to be using in this section. And so I want you to make sure that as we go through this section, go ahead and make a note card for each of these terms. So I would advise you pause now, get some note cards or a sheet of paper, and cut it up into flashcards so that you can study these terms. These terms are going to be used a lot in this section as well as throughout the rest of the class, so make sure that you know these terms. Okay, so we've talked about the word solution several times, and many of you have been using it correctly, but we really haven't defined what it actually is. Way back when we talked about homogeneous mixtures, meaning that they look the same throughout. That's really what a solution is. We kind of threw that word out back when we introduced that, but now is when we're really looking at the fact that we have a uniform composition and appearance. Everything appears to be the same within it, within the solution. So the total thing is called the solution. The substance that you have more of, the one that's going to be doing the dissolving, is going to be the solvent, and then the one that you have less of that you're going to dissolve in the other one is called the solute. That difference is very important, so make sure you do those flashcards and start studying them immediately so you can start to get familiar with those terms. You're going to be doing problems and calculations potentially, where it's going to say, oh, 3 grams of the solute and 12 grams of the solvent, but it's not necessarily going to tell you exactly what's going on. So you want to make sure you're becoming familiar with what that means so you can picture it. A lot of solutions are liquids, but that's not entirely the case for every single one. Air is a great example of a solution, which is gaseous. It is a combination of water vapor, carbon dioxide, oxygen gas, nitrogen gas, etc. So there's a lot of things kind of mixed in with air that make it an actual solution. But it is homogeneous. When you look around, you're not like, oh, wow, there's so much more carbon dioxide on that side of the room, because you can't really tell the difference, okay? Brass is an example of a solid solution. It's composed of copper and zinc, and they are melted down, put together, and made into a solid. So thinking about particles, when you're actually thinking about these, you want to be picturing what is actually happening here. So I'm going to start by breaking this apart, and we're going to have two situations here. Up here, we're going to have a situation where we have a couple particles of a liquid in here, okay, and then we have some solute particles mixed in as well. Okay, so with liquids, what we have is, because they're spread around enough, we have the ability to put things between the molecules of the water. However, the molecules of the water are still close enough and still have their hydrogen bonds, intermolecular forces unit 4, enough that they are capable of holding together in solution. So just because you put something into the water doesn't mean that it's automatically going to, spread out or not be able to hold it. That is an interesting thing about liquids. And then, the more that we spread these apart, if I had the same beaker, but I was able to spread them out even more, usually due to the fact that I'm heating it, okay, that means that I could actually fit more of these particles between the water. So that's an interesting thing about solutions that was going to kind of guide us into some other things here in a minute when we talk about how increasing temperature can affect how we could actually have a solution. By definition, concentration is the amount of solute that's in the solvent. So basically, we're looking at how much stuff we dissolved in the other stuff. Okay? If something's at a high concentration, that means we have a lot of solute with low solvent. This would be an example of something at high concentration. So the pink particles are representing the solute. The bluish, purplish liquid is the solvent. So we have a lot of those particles in there. Low concentration would be when we don't have very much. We also call that very dilute. And this high concentration, we call it concentrated. Okay. As you add more of the solute to the solvent, you get a higher concentration. You could affect it, though, by, let's say that this particular one over here, we're looking at as being very concentrated, but then we start adding more water into it. Okay. That would start to lower the concentration. So over time, the concentration might decrease if we were to add more to it. Consequently, if we allowed this to start evaporating and this water started evaporating off, we would become more concentrated. So you can kind of adjust the concentration of a solution in multiple ways. Again, here's another example of concentration, concentrated versus dilute, and you can actually tell sometimes with how it looks whether or not it's concentrated or dilute. Not all the time, but sometimes it is possible. Concentration is usually represented with the brackets, and what we mean by that is that if I'm saying the concentration of magnesium chloride, okay, then I would represent that just by putting brackets around magnesium chloride. Okay, so you might see us start doing that on the board. It's definitely going to show up when we get back from spring break and we're doing acids and bases. But that's generally what we mean by concentration. And sometimes because I'm lazy, I'm just going to use that symbol, just like you guys know that I use that symbol to mean change. Oh, if I can spell change. I can. Okay. The wrong concentration sometimes can cause things not to work correctly. An example being eye drops. Our eyes are very specific, and so it has to be a specific concentration of salts. If we have an increase or decrease in that, it could cause pain in our eye, and our eye drops wouldn't work for other organisms that have different concentration. So when a solute or solvent are put together, there's going to be a limit to how much we can put together. If I take a huge old glass of something and I just put a spoonful of salt in it, I'm typically going to have what we call an unsaturated situation. So an unsaturated solution is when we could easily put more solute into the solution. Saturated means we have essentially met the limit, and supersaturated only occurs if there's a change in temperature, volume, or pressure, but a supersaturated solution is a temporary situation where more of the dissolved solute than normally would fit is possible. And that is what gives rise to this. Okay? If any of you guys grew up in the South, or if you've been there, or even here, you can get sweet tea here, but if you've made sweet tea, you may know that you can never get it right if you add the sugar after it's cold. That's not possible. Okay? So the way to do it is to add the sugar while it's still very, very warm, while you're actually steeping the tea bag, because that allows you to get more sugar into it. So at a higher temperature, just like we looked at in the diagram a minute ago, at a higher temperature, we're able to actually fit more solute into something. So if we want something to become super saturated or extremely saturated with that solute, we would need to increase the temperature or change the volume and pressure. Temperature is usually what we do. Now, y'all couldn't get through this unit without some calculations. So molarity is how we calculate concentration. Okay, there's other ways to calculate concentration, but molarity is kind of the chemistry way of doing so. We'll talk about the other ones as well, and we'll do some of those. But molarity is basically the number of moles of solute per liter. Okay, so that is basically this. Molarity equals moles over liters. Okay, get that formula written down, and then let's look through a couple questions. So this question's asking about molarity, and it says we're looking at molarity of a solution made by dissolving 0.3 moles of calcium nitrate. So right now I'm going to go ahead and highlight this. 0.3 moles of calcium nitrate, and I'm going to highlight moles so I know that that's what that is. Okay. In enough water to make 5 liters of solution. So I'm going to highlight 5 liters of solution, and I'm going to go ahead and color liters. Okay. So that means that's exactly where I'm going to plug it in. Liters goes on bottom, so we'll put the 5 liters on the bottom, 0.3 moles on top, divide, and we get this glorious answer. 0.06 molar calcium nitrate. We say that by saying 0.06 molar, okay? So it's molarity, and we generally would say 0.06 molar. Like if something was this, we would say it's 1 molar, okay? So that just kind of gets you used to the vocabulary of that. The last example we have is a little bit more complicated here. In this particular case, we're not looking for exactly the same thing. In fact, in this one, I'm looking for how many liters of 0.5 molar sodium chloride can be made from 0.1 moles of sodium chloride. Okay, so looking here, this is blue, this is green, that's red. Okay, so what we have to do at that point is actually really work this out a little bit more in detail. Okay, so we would have the 0.0, nope, 0.5 molar equals 0.1 moles on top. On the bottom is x liters. Okay. We need to get the x by itself. Hopefully this is an Algebra 1 skill, but just going to show you how I'm doing it either way. It's currently in the bottom. It's in the denominator. We need to get it out. So let's multiply both sides by x. Okay. That gives us 0.5x equals 0.1. Divide both sides by 0.5 to get x by itself. That isolates x, and we end up with 0.2 liters, which is correct. Okay, so that's the number of liters that we would need if we had that much sodium chloride to make that concentration. Okay, and this is a real life calculation. This is what I do all the time when we have labs. I have to make the different concentrations of solutions, so I do calculations like this a lot. Okay, now of course, and don't get too excited, this is in moles, so it's definitely possible to convert to grams, and you might be asked to. Okay. All right, I'll see you guys next class, and in next class we're going to be doing a lab, and we're also going to do a little bit more practice on some of this molarity. Have a great one.